So therefore, focus here will be examples. Okay, so what are the characteristics? First of all, it is 12-bit. Second technology is 0.18 micron. It's a pipeline ADC. And it's cost effective because they have done it in digital process. So additional information, sampling frequency goes up to 110 megasample per second. Of course, supply voltage is 1.8 volt. One thing I tell you, like say when you say 12-bit, it may not be 12-bit for all values of input. That's a very important point. If you have a smaller signal, you may get better SNR. If you have larger signal, because of the distortion, your resolution may reduce. Therefore, usually number of bits are reported for a particular input. For example, practically ENOB is 10.4 for input frequency of 10 megahertz and 2 volt peak to peak. So when you increase the amplitude of the signal, your ENOB reduces, which is expected. And power dissipation 97 milliwatt. There is one part in the circuit that will be good if you implement. At first read it and then learn it. But it is not the main part of this because they have done some additional work. Because when you change the sampling rate, accordingly, like suppose if you use this ADC for lower sampling rate, then this means that your signal bandwidth is low. So lower sampling rate, for example, it can reach up to 100 megasample per second, but you may use it for some cases 1 megasample per second. Therefore, you may not need really everything, including Opamp, to have that settling time you need for 100 megasample per second. Therefore, why unnecessarily consume power? Therefore, they have a switch capacitor based current reference generator which scales the power according to the sampling rate. And this helps to avoid extra power dissipation. So that is not a part of your project, but it will be good if you implement it. If you implement and get results, you will get bonus in your project. But it is not compulsory. Okay? Implement means on silicon. Okay? Never use this word implementation. It is design. If you design it and you specify in your report that this is your design and these are your results, then you will get a bonus for that part. And if you don't get time, that's okay. You can use an ordinary bias reference generator because here we don't want to optimize for everything. Just you will do a practice because as I said, when you do it, then you will get at a scale. Okay, so now like some of the practical implementation. So let's see, like this is not a very low sampling rate and this is a good number. Okay, so how many stages? They have, eventually they have 11 stages, pipeline. And one way was, okay, to keep all stages same, right? Now here is a practical implementation. Therefore, all stages may not be same. Specifically, early stages and last stages can be different from middle stages. The reason is early stages are very important. Like every stage you have gain of 2. Therefore, your noise will get divided by 2. If you have, and we'll come to the input. So, every stage, if you go from one stage to the previous stage, your noise will be divided by gain of 2. And power-wise, it will be divided by 4. Therefore, first stage is a very important stage with respect to noise. Also with respect to linearity, because if you have some non-linearity, linearity is not scaled. And then you give it to the next stage, that delta V will get multiplied by 2. And therefore, it becomes worse. Therefore, linearity of first stage is very important. Noise performance of first stage is very important because it won't get divided by 4 again. It is the free input stage. So therefore, first stage has been very important for them. So therefore, they have made first and second stage a little bit different. Only main thing actually is with respect to sample and hold capacitor. And then last stage is a 2-bit flash, and they don't do any pipelining there because these are LSP side, and then just keep it. And 2-bit flash is okay for them. Therefore, you will have, I call it a stage 1, which is different, okay. Stage 2, again we'll have a different. Now, from stage 3 to stage 9 to stage 10. So, these stages will be same. So, in this way we separate them. And then finally stage 11, which is just simple 2-bit flash ADC. All these stages are 1.5 bit per stage. Okay, so these are also 1.5 bit, but because they are not same as others, therefore we make them separate. Okay, now you know what do we mean from 1.5. Okay, and then finally at the output, they will get by using same circuit. By the way, there is a notation which actually is not correct. That is called digital error correction. I mean, of course, this is used, that is okay. But, I mean, maybe we can call it actually. But this digital error correction, it's not calibration or something else. This is the same thing that we discussed before. Like in pipeline ADCs, what they do is that they generate redundant bits. And then out of those redundant bits, they generate main bits. So this logic sometimes is called digital error correction. So in this paper, particularly they call it again same name, but this is same logic that we have already. And they call it like, they say that this is delay elements, and these are just notations which are used in the paper. I am telling to you what does it mean. And digital error correction. But actually this delay element is same as register. And this digital error correction is that logic circuit to extract 12 bits. Okay, because you will have 2 bits at every stage. You have 10 stages, it's 20, and then plus 2 bits at the end. But you will extract this 10 out of 20. Plus 2 will be 12 bits. Okay. So because of noise issue, for first stage, the whole capacitor is 1.5 picofarad. So this is 1. For the second stage, it is 1 picofarad. And then for remaining stages, it is 0.5 picofarad. So they also mentioned that if suppose you would have used 1 picofarad for all stages, definitely you would get a better performance. But here they are just reducing these capacitors, and they say that the amount of degradation you get is acceptable or has been acceptable for them. Therefore, they have reduced capacitors to 0.5 picofarad from stage 3 onwards. Okay, now if you remember, we had this track and hold and with offset compensation and then multiplication by 2 everything and sampling everything in one stage. Do you remember? It was a switch capacitor based amplifier, but it was just simply amplifier. But this is 1.5 stage per bit, bit per stage. Therefore, you need to have 3 cases, right? And this is differential. Therefore, that's why I just explained for you how it works. So, eventually at the output of every 1.5 bit, This is what is written in the paper. Okay. Of course, we are talking about the bandwidth of the Opamp. If bandwidth of the Opamp is very large, loop gain. If loop gain is very large, then you can have this output almost this. If loop gain is not very large, you will get this term at the okay. I use notations which are used in the paper, it's better. So this is loop gain. Okay, if your loop gain is not very large, this term will get multiplied by this residue term. Okay, and then Vx. So these are all notations used in the paper so that you will be able to follow. We reference P means positive, or we ref N, or 0. So what kind of conversion it would be? So we had it. I just show you here in the previous slides. So this was for single-ended. So do you remember this was for single-ended? If we have 2 bits per stage. Now if you want make it differential, shift this plot to left and down. Okay, so that instead of 0 to V full scale, you will have between minus V full scale by 2 and V full scale by 2. So you will get this. Okay, this is for differential. So this Vx actually will be Vref P or Vref N, and Vref P and Vref N are actually V full scale by 4 and minus V full scale by 4. For example, okay, this is just an example, and 0 anyway is 0. So this is to clarify exactly what kind of levels are used in this particular reported work. Okay, so till now everything is as according to what you have learned. Now we want to implement this again using similar switch cap configuration. One thing I didn't find in this configuration was offset compensation. Now you will see that doesn't have offset compensation, but we can easily have change arrangement of switches the way we did for the example in the class and make it with offset compensation. In the paper, offset compensation is not considered, but in your project you do. So therefore let us make a note. Let's make a note for the project. One is offset compensation. So offset compensation of course will be for both cases, SAR ADC as well as pipeline ADC. But switch cap reference current generator is optional will have bonus if you use it, do it. Okay. So now again there will be 3 phases of clock. I try to save the paper, but it is same as what we had before. Do you remember we had 3 phases? Phi 1, Phi 2, Phi 3. And in fact, one of the phases was just to avoid input dependent charge injection. So here also is same thing. So they have actually 3 phases, but mainly 2 phases. So they call the second phase, which is actually based on phase 1, is Phi 1b, which will go to 0 a little earlier than Phi 1. But it is simultaneous in the rising edge. It's something like this. And then Phi 2, they have shown it actually as a completely complementary case, but could be, this is what is shown in the paper, but actually could have been a little non-overlapping. So at least in this way, it is, in this way it will be a little non-overlapping. But eventually it can be completely non-overlapping, Phi 1 and Phi 2. So these are same as this is the way it is shown in the paper, but you can consider Phi 1 and Phi 2 to be completely non-overlapping. And it's better. Okay, so there will be one stage which will be track. Again here, when a phase is 1, corresponding switch will be closed. So we have always this convention. And if a phase is 0, corresponding switch will be open. So I don't write it here again. Okay. Switch. So when a phase is 1, corresponding switch is closed, and then this is one phase. Because the circuit is given in the paper, I don't draw everything. I just show you what happens during these 2 phases, which are different a little, but it's very, very similar, very actually similar to what we had before. So what they are showing in the paper, they are showing 2 capacitors with common bottom plate. So that's why capacitors are connected between bottom plate. So this is bottom plate here, and then they are showing 2 different capacitors in this way. So it's same thing. But they say that when you go to layout, you can make bottom plate of all of them to be same actually. That's what they are showing in this way. Now in phase Phi 1, so these 2 switches were closed. So that's why this shows switch is closed. Connected to Vin plus, this is a fully differential architecture. So C1, C2, again C1, C2. Okay. And they are connecting bottom plate of both of them. Oh, sorry, both are 1. So that this switch also is closed and connected to it. They call it the common mode. So see here, notice this V in K actually is differential input. And output also differential. Okay, VID, VOD. So it's just differential input. It's the only difference. Okay, so this is common mode. So means that if you look at single-ended input, it is a signal which is always positive. So you have a common mode. Negative input, positive and negative input, both are always positive, above 0, because you have a common mode level. But when you get the difference, you may get positive or negative difference. Okay, the same thing we have in differential circuits. So this is Opamp. Your feedback factor, of course, is 1/2. Okay, so this is very similar to previous case we had. This is track and hold phase. In fact, it is tracking, it's still not holding, because if input changes, that also will change. But this tracking phase, if you notice, two inputs of Opamp are shorted together. That's why it doesn't have offset compensation. What we could have done, in fact, the correction you can do, same as what we had. You open inputs, and then you keep Opamps in the unity gain feedback mode. Therefore, now you will have offset also stored on the capacitors. Same thing that we had before. Here they have not done. This is short circuit and Opamp is the open loop mode. Actually, it was my question, why they have done this. This doesn't look, I don't know, what is the reason behind that? Because we would prefer to put 2 capacitors in the feedback loop and then, not capacitor, just direct connection, unity gain feedback, remove this connection, and then this is a deamp, therefore inputs will get connected to common mode internally using common mode feedback, then you will get it. I don't know, maybe their Opamp, so this you check from paper. So this will remain a question mark, okay? Why do we need? Because this doesn't solve the problem of offset. And then in the next step, when you want to go into hold mode, which switch will be open first? This switches or this switch? This switch, by the way, is controlled by phi 1. So therefore, this also will remain as a question. Okay, if answer is not found in the paper, therefore you do it with offset compensation. Okay, so now which switch will be open first? Corresponding to phi 1b or phi 1? Phi 1b. Why? If I don't take VCM, because then the bottom plate will be in a floating state, right? It will be a floating node. Therefore, there is no chances of charge injection. So therefore, phi 1b goes to 0 first. So you will have an intermediate state, which will be this. In this intermediate state, same as before, nothing happens. Nothing happens, nothing changes. But there will be no charge injection. And then now you will go to this stage. Okay, so this is intermediate stage, nothing happens, and this is hold state. Okay, so therefore phases are same as example or case that we had in the lecture previously. Only now how it will generate this 3-segment transfer characteristics, right? We had 2 segments. Now we want to divide it into 3. Therefore, it will depend on the status of the logic bit. Okay. Now we go with this state. So in this state, what should happen for C2? This is hold mode with gain. Phi 2 is used to generate hold mode. What should happen for C2? Then we will find location of Phi 2. Yeah, C2 should be connected in feedback. Therefore, Phi 2 actually should be used to connect C2 in feedback mode. Yes. So therefore, C2 will be in feedback mode. So Phi 2 actually is connected here to the top plate of C2. So that when Phi 1 is open, corresponding switch is open, that switch will be closed and will connect it to the output. So therefore, this will be the condition for the. So I don't redraw everything because these are already known by you. I just show how this difference happens. And I recommend you divide work between you and your partner. It will save 50% of your time, and then you club them together. The same way you do your other projects, like your MTech project. Many students do a piece of work and then we club them together. So you can also do same thing. I'm just showing this direction the same way. So okay, so the same strategy which was used to write equations in the previous. Okay, so because why I am using this V1 plus V1 minus? Because I want to show that in general we generate it as a function of a voltage called V1 connected at the input, and this V1 is actually either 0 or Vref P, Vref. For example, here Vref by 4 or minus Vref by 4. I mean in the way it should. Okay, so therefore this is V1 plus V1 minus. We write it as a function. So shall I write equations or not? So it's same as before, C11 equal to C12 equal to C1, and then C21 equal to C22 equal to C2. And then you have initial condition, right? We consider that a little before connection of switch corresponding to Phi 2, which keeps C21 in the feedback mode and C22 in the feedback mode, that is time equal to 0 minus. So you will write initial condition. Okay, what is initial condition? Before you connect C2, what is stored here? V in minus, V in plus minus. VOS? Okay, offset. Yeah, here there is no offset because previous case we have. Fine. Suppose if we have, yes, it will be V offset by 2. Minus VCM. CM itself has by 2, yeah, inside. Okay, correct. So therefore this will be V in plus. Here, because they have not used any offset compensation, it will be like this. But as Yaman said, if there is an offset compensation, therefore here, as per our notation, we write it in this way. So therefore, I don't write it because that particular configuration doesn't store V offset. We need to keep Opamp in unity gain feedback. So, and then, okay, VC 1, 2, okay, this was the original value which was stored. It was in the tracking mode. So this voltage now is stored here before it goes into holding mode. And then when it goes to holding mode, now you will have a transfer of charge from C11 to C21, and of course now these inputs also are connected to V1 plus, V1 minus. So again we use that charge transfer principle. So amount of change in the charge stored on the capacitor C11. So now new value will be V1 plus minus V common mode. Original value was V in plus minus V common mode. So this is the amount of change for capacitor C11. Then this will be minus, because now it is an opposite polarity is connected, minus C21 into again change in the charge. Now it will be V out plus, that we want to find out, minus V common mode minus original value which was V in plus minus V common mode. So the same thing you do for the other one, which will be versus V in, V1 minus, V out minus, V in minus. So therefore finally you will get this. V out plus is equal to C1 plus C2, V in plus minus C1, V1 plus upon C2, and V out minus is equal to C2 plus C1, V in minus C1, V1 minus upon C1, upon C2. So now if you look at this transfer characteristics, so according to the generated bits 0, 0, 0, 1, 1, 1. We have 3. This is also 0. So as you see here, you know, if I make C1 equal to C2, suppose for example, C1 equal to C2, right? And here what we need is that to make either 0 minus V full scale by 4 or V full scale by 4, right? So accordingly V1 can be connected. So how they do it, they have a portion which actually generates this logic bits, right? I come back to the paper. Decoder and switching block, they call it DSP. So they had reference P and reference N. So this reference and reference P will be decided according to the logic bits which are generated here. And therefore here what is connected this side to the bottom plate will depend on the bit which is previously generated. So, therefore, according to the current bit, either it will be 0 or it will be Vref by 2 or it will be minus Vref by 2. Means that either here you will have 0 or Ref P or Ref N. Again here you will have 0, Ref P or Ref N. Here they are showing Ref P, Ref N. But actually Ref P and Ref N can have 3 values. These are connected during hold mode. Because when you are in the tracking mode, this will get disconnected and then input will be connected to the signal, which is coming either from directly input or previous stage. Yeah, there is a switch inside. That's why it says that decoder and switching block. Because we had only binary, multiply by 2. We had only a gain amplifier. We didn't have shifting. Here we are adding and also we have adder as well as multiplier, right? Actually it is like that. Yeah, in fact we add and multiply both. See, in the example we had, I don't remember which lecture it was, a few lectures back. This V1 plus and V1 minus was 0. So we had only a multiplier. So you would have had only connection to common mode level. But here you need to have this adder. And because of this you need to connect these switches to Vin plus or Vref P or Vref N. Okay, so as I said, I try to make it as close as to what you have learned in the lecture. One thing also I tell you, like see, as I said, if really we want to cover everything, we should have a mixed signal 2 also. But one thing is important, when you know the concept, then see, this is a sample paper, right? Now you are able to understand the paper almost, and if you read it, you will see it is easy for you. So now if you come to other architectures, it won't be very difficult. Now I give you an example. Means that because you know the concept of data conversion, main characteristics, how are these main architectures are used. So now if something new comes, then it is not very difficult for you to understand. Now let's see, for example, in SAR ADC, another paper. Okay, before going to that, just one thing I mentioned, we need to add to our, this is also simple, you will see this switching arrangement to reduce on resistance. This is that switching bias generator. Okay, interesting. NL, DNL plots are not given, but SFTR, SNR and SNDR are given. And again versus input frequency versus conversion rate for a given input frequency. Okay, so see, regarding what you need to consider for your non-idealities. Of course, Opamp is not an ideal component, therefore automatically you will get all non-idealities associated with Opamp, for example, finite gain. But one thing you need to see how much offset now or mismatch we should consider. So the amount of mismatch that you can consider will be 0.05%, okay, as an initial value. However, what I want you to do is that you generate mismatches by some value which will give you almost similar characteristics which are given in this paper for SNR, SFTR. So we will do a reverse operation. Means that we want to see that how much mismatch really can lead to this kind of characteristics. But you have two kinds of non-idealities. One is Opamp non-idealities, and of course Opamp offset that you will compensate. And then another non-ideality will be mismatch only. So just a small mismatch between these two capacitors, very small mismatch. And that may not, we don't know, because that really determines your gain per stage. So see really how much this amount of 0.05% mismatch, how much will give you non-ideality compared to the case you don't have any mismatch. So first you can just consider you don't have any mismatch, you derive all plots And then you apply this 0.05% mismatch. Because now this is change in the gain of the every stage. Ratio of two capacitors. Okay, so that's what we want to do is you reproduce these plots. Okay, reproduce these plots and then see how it is different from your results. We want to have a one-to-one current comparison because non-linearity plots are not given directly, that is fine. So you don't need to generate them. Then you focus on these characteristics. In SAR ADC, it is given, therefore it is good. Therefore you will have two kinds of simulation. Okay, for example, let's see. For example, here you hear a new word, time interleaving. Look at the title of paper. Can you guess what is time interleaving? Right? We didn't have time interleaving. That's very easy to guess how it will be. Look at this architecture. Can you see that? Shall I zoom in? There are two SAR ADC. Okay, and these are C network. In fact, that is that binary weighted capacitor array. So what can be time interleaving? So what was pipelining? Pipelining was to generate some number of bits per stage, and when one stage is doing its job, it's just focusing on 2 bits, and next stage is processing the previous 2 bits which have been received, or 1 bit or whatever, and so on. So it was helpful to improve throughput or sampling rate of ADC. So there is one way more that you can do, because processing always takes time. In pipeline, if you sample input signal, okay, at the first stage you need to sample input signal, give it to the first stage. Other stages don't need, because automatically the track and hold is done during this mechanism of multiplication, as we saw. So therefore only first stage needs a hold signal. So what would be the sampling rate at the input of first stage compared to sampling rate at other stages for a pipeline ADC? They are same, exactly. They are same. You are sampling with the same rate that you at stage 1 as sampling rate at the stage 2, 3 and 4. Therefore, your sampling rate is uniform across all stages. Now, suppose you could have had a very fast sample and hold circuit at the input of first stage. You could have had, but you cannot use it. The reason is because even if you sample it very fast, every stage should have that enough time to process, generate bits, and then now receive the next sample, right? Therefore, you are limited. Now, suppose what you can do to use this excess sampling rate that you can achieve. That is where you can interleave stages. So, interleave is different from pipelining in the sense that in pipelining, you will use same sampling rate for all stages. In interleaving, you will use a higher sampling rate at the input. Now, if you have this higher sampling rate, what you will do? You have, for example, 2 ADCs, and each one of them is operating at sampling frequency of Fs. But actually, you can have sampling frequency of 2 Fs. So, therefore, you sample, but you give first sample to upper one, second sample to lower one, again third sample to upper one. So first ADC will receive odd samples, second ADC will receive even samples. Now at the output you use a very fast MUX, right? Very fast digital MUX, which is operating again with 2 Fs. Therefore practically you have achieved 2 Fs sampling rate using an ADC which can work at Fs, right? So it is something like TDM, very similar to TDM in logic, in even communication. So therefore this is the difference. So you know, as soon as, that's why concept, if you look at abstract levels, concepts are easy to understand. Only the way they are implemented is challenging, because now you need a very good sample and sampling circuit at the input and then very fast mux at the output. And usually the input part is more challenging compared to the fast mux, because fast mux can be implemented. So therefore, for the second half of the students who will work with, it's actually a SAR ADC. And it's just interleaving, just adding, you design one stage and then just put them in an interleave manner. So therefore, then that would be interesting, because you are achieving twice of this. And it was very interesting. I'm looking at, do you remember there was a talk by NXP research, what was his position? Research director, manager, something, a couple of months ago. So he is actually designing this kind of SAR ADCs with time interleaving architecture to generate a good resolution as well as a good speed. This is one way of improving the speed of SAR ADC. So, and then the remaining part is very straightforward, because as you can see, again, this is only differences, it's a differential architecture. In the class, we covered single-ended architecture. So, just is an interleaving. Okay. And then there is a black box here, which is called bootstrap switch. So, bootstrap switching is not explained here. Again, bonus for group 2. Again, you are not forced to use this switching. You can use simple switching. But if you do it, then you will get a bonus. So first you need to look at the bootstrap switching. So it is optional, but it's bonus if you do it. Otherwise you can use simple switches. At least in simulation you may be able to achieve the speed they are talking about. It's 6-bit, the resolution is half of that pipeline, and sampling rate is twice. Because for high sampling rate, you cannot achieve the resolution usually pipeline can give. Okay, and okay, to explain you this also. There is a very interesting, because it's good always to have something different from what till now you know about this structure. Okay, so this is, first of all, this is differential. That is the reason you have the VIP, VREF. Okay. And then you want to decide whether VIP is greater. So by the way, here is not explained, but I tell you, this arrow is no. Okay, top arrow is no, bottom arrow is yes for every decision. Like VIP minus VIN is greater than 0. This is actually, it's better you call it, you write it in this way. VIP, is VIP greater than is VIP minus VIN, which is VID. Is VID greater than 0? If answer is no, it will go here. If answer is yes, it will go here. Again here, whether VID is greater than minus VREF by 2. If answer is no, it will go up. And if it is yes, it will go down. Okay. And then you see that the switching arrangements are exactly opposite for positive and negative. So I don't rewrite equations because it takes time. We have shortage of time. But if you have any question in deriving how it works, you just tell me next lecture I will derive. The same way I derive for pipeline. But it looks very easy because as you remember what we were doing, we were connecting to ground, right? Or common mode and then deriving this divide by 2. So here also is doing same thing for positive and negative and so on. Now what they are saying that because now you have double of this capacitor arrays, you need to do switching twice for each half. It unnecessarily creates a lot of switching and a lot of power dissipation, dynamic power dissipation. So what they suggest is that change it in this way. You only change the upper one or you only change the lower one. Don't change both of them. Okay, here I think there is a Mistake. This should be connected to, okay, no, this is actually, yeah. This is reset initial phase when you keep Vi minus Vref on capacitors. Then you remove Vi. Now you will go to this decision making. Whether VIP minus VIN means VID is positive. If it is no, you will go here. Now if you notice, you will have only one transition. They are keeping one side constant and one side only connected to ground. So here you had both sides switching. And this saves power. Also it has another benefit. If you notice, you have only connection to ground. And when you have connection to ground, you can use only an NMOS switch. Because NMOS switch can handle low voltages. You don't have any problem. And then when you have NMOS switch, you will be able to achieve better speed. So this is explained in the paper. Therefore, you use the switching mechanism which is explained. Actually, it's not required to switch both of them. Number of capacitors are different. Why? Because I don't know. I'm not sure. If they are saying that for the same number of bits, that's the question. If number of bits are different, yeah, then it can be. I don't know. You just check the paper. They say for 3 bit. For 3 bit, we need C, 2C, and 4C. For 3 bits, we need 3 values. C, 2C, 4C. Yeah, C means we need C values and 2C values and 4C values. You check the paper. That was a good question. I don't know. It is good if actually they can. How they can? What will happen here? Oh, maybe. Because you are switching only one side. For example, if you want to generate Vref by 2. Actually, I think here what happens is that, to generate Vref by 2 in the upper one, which is differential, you need actually to generate, say, for example, Vref by 4 and minus Vref by 4. Or 3 Vref by 4 and 1 Vref by 4. Upper side, see, look at upper one. Upper one will give you 4 plus 2, 6. 6 upon 8, 3 by 4. Right? So upper side will give you 3 by 4 Vref. Lower side, I'm just using the capacitor division. Do you understand it? Who understands it? Who doesn't understand? See, you want to compare VID with Vref by 2. What is VID? Come on, what is VID? VIP minus VIN. Okay. You want to compare VID with Vref by 2. What is VID? VIP minus VIN. Means that voltage at the positive terminal minus voltage at the negative terminal. Now look at capacitive division. In upper side, what you will get here? 3 Vref by 4. Right? What you will get at the lower side? Vref by 4. Difference will be Vref by 2. So it is comparing VIP minus VIN minus Vref by 2 by 0. It's comparing it with 0. It's VIP minus VIN minus Vref by 2. It's comparing this with 0 at the input of comparator. Now come to lower one. So what is upper side? Untouched. 0. What is lower side? Vref by 2. That is the reason they are using less number of capacitors. So they are achieving same thing but with less number of capacitors. And less switching and less power dissipation. They have also analysis of energy dissipation. It is obvious, right? because you have less number of switching to VREF. Look here, for example. This capacitor 2C was grounded. Now, if you go to down conversion, you will get VREF, or actually up conversion. Means that it will be greater than minus VREF by 2. It will be connected to VREF, you will draw power from VREF. But then now you will have less number of switching here, because one side will remain constant. So they have also analysis of energy dissipation. And then comparator architecture. In the previous example also a pump structure is given, you can use same architecture. It was a folded cascade. Here is the simple, again see a PMOS differential in regenerative load, 2 inverters at the output, and these 2 are used for pre-charge, to pre-charge to 0. It's very similar, and it has actually only one regenerative stage. So these are both papers are very good papers. This is energy analysis, then comparator design. Everything has been explained very well. Okay, so I think with these 2 examples, you don't need to make a layout, by the way, that's okay. You will do only at the schematic level. And then you will make a table similar to this. Okay. Oh, yeah, for that, it's not a big deal. See, for example, DNL, INL, I will get back to your question. DNL, INL are given here. See really how much offset can lead you to these values. And here I think they don't have, do they have? They don't have. They have not reported offset compensation. See, for SAR logic, okay, one question. Do you know VHDL? Is there anybody who doesn't know VHDL? Just for the entire control logic. And then use mixed mode simulation. In VHDL, see, essentially in a Spectre, what you can do is that you can have an analog module and use a SPICE language. And then you can have a VHDL module and then use VHDL module inside the Spectre. So now what it does is that it will do a mixed mode simulation. So some part will be handled by Spectre, the remaining part by that. You don't need to implement it. You can just use VHDL for the logic part. Same thing will be valid for pipeline ADC. Therefore, you don't need to design and then really make the schematic of logic part, because this is a straightforward work afterwards can be done. The main focus will be on the analog part and of course switching part. Okay. Yeah. And of course that logic which finally generates 12 bits out of 10 bits out of 20 bits. So see, for this it is only 6 bits. But for pipeline it is 12 bits. But at the same time for pipeline you repeat samples. I mean, having more number of bits is not very complex, right? Having 3 stages or 5 stages are same, you just copy them. Right? In your VHDL code also now you will have more number of repeated structures to generate that. It is XOR, eventually it is this adder. You will use adder, at the end you will have a subtractor, the same way which was explained. So I think this project will be very interesting. Both projects are good. You have learned the entire background that you need for these 2. And then when you are doing it, is just like you have reviewed the entire ADC content of this course. So I don't continue with ADC. For DAC also, like the basics you know now, it's like for example charge distribution DAC and other architectures like current steering, that they are very straightforward, right? You have n number of current sources and then put switches, and then issues are similar in all of them. So as I told you at the beginning also, and now you understand, ADCs and DACs are very simple in the concept. What make issue in their design is non-idealities, which are related to switching and related to mismatch and variability. So we will stop here, and then from next session I will start on PLL and DLL.